Alright, this video lesson is on Newton's third law and also incorporates a discussion of physical systems. Here are your objectives. So Newton's third law often gets stated as for every action there's an equal and opposite reaction, but I prefer to think of it in this way, that forces only ever exist in pairs. And that's really the key idea. Whenever A exerts a force on B, B exerts a force of the same magnitude, but back on A in the opposite direction. So a couple things, same magnitude, opposite direction, and notice that those two forces in the pair are acting on different objects. One's acting on B, and one is acting on A. The reason I don't really like the action and reaction description is it makes it seem like one is happening before the other. It kind of implies in my mind that action happens and then there's a reaction, as we usually use those words. So I prefer to think of it as forces always exist in pairs. If there's a force of A on B, there's an equal and opposite, that's the opposite, force back from B onto A. Those forces are of the same kind, so if one is a normal reaction force, then the other is a normal reaction force. In other words, if this is a box sitting on a table and there's a normal reaction force acting from the table up on the box, well, there's also a normal reaction force from the box acting down on the table. Both gravitational forces, both frictional forces. Let's take a quick look at gravitational forces for a moment. If you're standing on the Earth we know is acting on you to pull you downwards, but you are also acting on the Earth, and we can imagine the center of the Earth there, to pull the Earth upwards. So those are the Newton's third law pairs. It can be confusing, and sometimes we think that the Newton's third law pair for gravity down on you is the normal force up on you. That's not the case. Okay, so again, forces always act in or exist in pairs. Here's a quick example. We've got an astronaut of a given mass pushing on the space station of a given mass. Draw the free body diagrams of each if the astronaut pushes off the ISS with an average force of 200 newtons. So this is really just the first part of a question that could then ask us about their accelerations. But if that's the free body diagram for the ISS and that's for the astronaut, what it means for the astronaut to push off the ISS with a force of 200 newtons is that there's a Newton's third law pair between the two objects, the astronaut and the ISS, both of which are 200 newton forces pointing in opposite directions. Okay, again, a 200 newton force acting on the space station is going to cause a much lower acceleration being equal to F net over m. It's going to cause a much lower acceleration than on the astronaut because of the big difference in the mass of the ISS and the mass of the astronaut. But the magnitude of the force is the same. Okay, let's carry on with a discussion of systems. I've already shown you a picture like this. I want to emphasize that we can group objects together when we're analyzing physics problems, and that group we call a system. And everything around that we call the surroundings or the environment. And this is really your choice. You can determine where the system is, and we will want to do that strategically to solve problems. For example, let's say that I take this person and mentally isolate them from everything. They are the only object in the system, and everything else is the surroundings or the environment. Now, anything within this system now, any forces acting within this system are now an internal force. If this person pushes on their own head, that would be an internal force, and I'll talk about what that implies in a moment. But something outside of that system would be an external force acting on this person. Now, we could change it, like I just described above. We could include, for example, the Earth in the system. And we actually kind of unknowingly do this every time we talk about gravitational potential energy. Because gravitational potential energy requires us to think about the arrangement of an object, in this case a person, relative to the Earth. And so what we are actually doing there, even if we don't realize it, is we're drawing that mental circle around both the person or the object that we're talking about on the Earth and the Earth itself. Otherwise, we can't really think about gravitational potential energy in the same way. Couple of other examples. Let's say you had two boxes with a rope in between them. You could think of the two of them as one system. And if you were to do that, then in this case, the tension is inside that system, and the tension is an internal force, therefore. It is within the system. And that means that this internal force of the tension can't accelerate the whole system. The tension here doesn't accelerate both boxes together. However, in solving the same problem, we might at some point want to just isolate one box on its own. And now if we draw our mental ring around that box, now in this case, tension is now an external force because it is acting on this from the outside. It's not the rope and the other box are not included in the system. And now the tension is an external force. And so the tension could accelerate just the leftmost box, but not the whole thing. So these kinds of mental shifts can help us in solving problems. This is another example, and if we had let's say we had two billiard balls that were going to interact. If we draw our box or our ring around like that, now the force acting from one onto the other when they collide is an internal force, and therefore it can't accelerate the whole system. It can accelerate either one of these, but not the whole system. And we will see more of this and delve into this deeper when we talk about momentum and isolated systems. So to summarize, a force between objects in the system is called an internal force, and it cannot make the whole system accelerate. That's why if you look back at the example above, pushing on your own head cannot make you accelerate forwards or backwards. It's an internal force to the system. It can't make your center of mass accelerate. Only external forces coming from outside the system, can make the whole system accelerate. So that's a quick introduction to Newton's third law and a discussion of systems and internal and external forces.